Using a rational function to describe a cost-benefit model is a very common application of this type of function. In this example, we have the function f of x equals 120x over 100 minus x. And this rational function is being used to model the cost f of x in thousands of dollars to remove X% of the pollutants that a city has discharged into a lake. Now, the obvious application here is that we would want to remove all of the pollutants from the lake that the city has discharged into a lake. But this function is designed to balance that want against how much it would cost to actually engage in that goal or to actually achieve that goal. So a couple of quick examples just to put our head in the right space. Let's look at what if we wanted to remove 20% of the pollutants from the lake. We use 20 in our function, 120 times 20 over 100 minus 20. That's 2,400 divided by 80, which is just 30. So 20% of the pollutants, we're going to need to use $30,000. Let's say we want to up it to 80% of the pollutants. So we'll use 80% as our input, 120 times 80 over 100 minus 80. Obviously much less of a divisor and a much larger numerator. And you can check the simplification on this, but you should get 480, which means that 80% of the pollutants, removing 80% of the pollutants will cost $480,000. Now, if this model was actually being used in a realistic situation, an actual city was attempting to clean up its lake with this model, they would have to balance the want of removing the pollutants with the cost. And clearly, there becomes a point where for a small town, a small city, it might be cost prohibitive to just say, let's clean up the entire lake, or let's clean up as much of the lake as we possibly can. And that point becomes very obvious when you look at the graph. If you have any familiarity with an exponential graph, this graph should look familiar. This is obviously not an exponential graph. It does not follow the rules of an exponential graph. The variable is not in the power, but it has that look to it, where at the very beginning, there's a lot of very small growth. Not a lot of increase in this beginning parts of the graph. But as you get to around 40, 60, 80 is where you start to see those really large increases that if you kept going, it would become cost prohibitive and it really wouldn't be worth probably the city's money to try to clean up all of that. The last part of this that we really need to worry about, and really need to spend a little bit of time thinking about, is what if we actually did want to clean up the entire lake? What if we tried to use 100? So we sub that number into our function, 120 times 100 over 100 minus 100, and right at this moment, you should have recognized that there's a problem. You are not able to put in 100 to this function as it is not part of the domain of this function, completely ignoring cost and pollutants and the city and all of that. If I just gave you this function and you just looked at that function, it's fairly obvious that 100 is not in its domain. So how does that show up when you're actually considering it against the pollutants and the cost and the city and the changes they would like to make? Well, if you look at our graph, it's fairly clear that here on this 100, this graph is never going to touch this vertical line. We're going to see continued increases in the cost, and we're going to see it never actually reach this line. Practically speaking, that means we're never going to be able to clean the entire lake. There will always be some kind of pollutant left in the lake. Mathematically speaking, we're never reaching that value as part of the domain. We would see continued increases in the cost as this function approaches that line and it points upward. We see continued increases in the cost even with just small increases in the domain, or small increases, in the X values. This is not a situation where you're cleaning up the entire lake. You're probably looking more at this space in here. And you're saying, at what point can I reach it where I'm still within my budget, but cleaning up a respectable or representative part of the lake? You really have to spend time thinking about, if you're using the rational function as a model, why is a particular value disqualified? Why does it make sense that the 100 is is not part of the function? Well, the mathematical explanation is because 100 minus 100 is 0. But the practical explanation is that it would be very difficult in a real world setting to clean up the entirety of the lake, to remove every pollutant from the lake, which is why you see this sharp increase in the cost at the end. We're not just going to continue increasing at a really low rate until we reach the 100. It would be really nice if the function just went like this. And then eventually we got to that 100 point, and it wasn't super cost prohibitive if we wanted to clean up the entire lake, and we could assure that it would stay clean. We have the unfortunate reality that this function is going to continue to climb this way and climb this way and see that prohibitive growth. So there has to be a practical explanation to these rational functions. That's the cost in the lake and not really being able to reach 100%, along with the mathematical explanation. But the best part about doing this is that they do fit together. There wasn't something contradictory happening. It wasn't like, oh, I can clean up the entire lake. Let's see what I'm at 100. It doesn't make sense. The function is designed to not reach 100 because it would be impossible for us to clean up the entirety of the lake. So when you're using a rational function, make sure you're balancing those two expectations. You have the very practical expectation of, does this make sense in a real world situation, versus the mathematical expectation of, I know 100's not in the domain. What does that mean for my analysis of the function?